Okay, before I do this, let's talk through a one proportion z-test, because again, the order and the general idea are the same. So if you were doing a one proportion z-test, the only one we know how to do, what is the first thing that you do? You write some hypotheses, right? You have a null hypothesis that would indicate there is no change, and an alternative that indicates there has been some change, right? Then after the hypotheses, you check the conditions. So again, all the conditions are the same. You have to check them for both groups, and I said you had to add in the clause saying that each group is independent of each other, right? So you check the conditions. After we've checked the conditions, what do we do? Right, so we make a statement, right? We say, because the conditions are met, we can perform a, in this case, two proportion z-test, and we can use a normal model, which in this case is the sampling distribution model for the difference in proportion. Okay, it's a mouthful, I get it. After you've made your statement, what did we do in the last test? Well, yes, we got a p-value. We got to do a lot of stuff for the p-value. Standard deviation first, right? And then z-score. And then to get the p-value, you find the probability of the tail, blah, 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 right? And we got a p-value. Once we had a p-value, what do we do with it? You make some conclusion, right? If it's high, we fail to reject. If it's low, we reject. All of that stuff is still true. Okay? Yeah? So the general idea today, the exact same. Okay? I'm going to twist a little bit of the stuff we learned yesterday, just a little bit. But otherwise, in general, it's the exact same. The reason it takes long to get through this, though, it's the first time you've seen it, so you have to make sure we go through it and know what you're talking about. It should be better this time, because you at least have some frame of reference, because you've seen a one proportion z-test before. So, you start with hypotheses, right? Now, our null hypothesis, again, is no change. That's what we're always looking at. There's no change. Well, for two proportions, we're always doing the difference between the two proportions, right? P1 minus P2, like we did yesterday. Find the difference in proportions. If you're assuming there's no change, then what do you think the difference is going to be equal to? We talked about this a little bit yesterday with confidence intervals. If what was in our interval, did we say there was no evidence? If what number was in our interval, did we say there was no evidence of something happening? 0, right? If 0 was in our interval yesterday, there was no evidence of something happening, because that means there's no change. There's no difference, right? So that's where we're going to start here with our null hypothesis. Okay, so our null hypothesis, it's always that there is no difference. So if you're going to write that in symbols, P1 minus P2 equals 0. Now, the one I highlighted, you'll see that every once in a while too. I don't like it because other things we do in our test. It's not wrong to write that P1 equals P2. I mean, that's generally the same thing. But for other things we do later, I think it's nicer to have it as P1 minus P2 equals 0. It will always be that. You aren't going to have anything else. Your null hypothesis is that one group minus the other group equals 0. Okay? Yes? We okay with that? Then we have to have an alternative. So the alternative is the exact same thing as we had before. We already have greater than, less than, or equal to, or not equal to 0. So do you think the difference is greater than 0? Do you think the difference is less than 0? Do you think it's not equal to 0? Okay? Same general idea. Everyone go with that. That's always going to be your null hypothesis every single time. Good? Okay? Now, we saw this yesterday. This is our standard error formula, right? Okay? So, even though we were subtracting, we're adding because you don't subtract standard deviations, right? We talked about that. Okay. Keep in mind, in our test, one proportion z-test, for example, we assume the null hypothesis is true all the way through it, and we used actual P all the way through the test, and then if the p-value was low enough, then we're like, oh, this is shocking and surprising, based on the fact that the null hypothesis was true, right? Yes? So same thing in this test, we're going to assume the null hypothesis is true all the way through, right? Our null hypothesis says that the proportions are equal to each other, right? So we should only have a single value of p hat in our standard error formula because we're saying they're the same. In our null hypothesis, we're saying the difference is 0, which in turn means that they are the same. So that's why they're trying to be all cheeky with the everyone into the pool, because on the next slide, I'm going to show you we need to pool the values. So we're going to put all of the data all together into one big pot and find one proportion. All right, that's the way we cheat around this to show that the proportions are the same. So to find that one proportion that we're going to use in our standard error formula, you're going to take the number of successes in the first group, add it to the number of successes in the second group. These are counts. These are not percentages. Then add the sample sizes together and divide. Okay, so we're pooling all data together from both of the groups. So instead of having P1 hat and P2 hat, we're going to pool it all together to make one. Yes, it's combined. They call it pooled, but it's really just combined. Again, the whole purpose of this is that we go through the test saying that the null hypothesis is true. And in this case, that means that the proportions are the exact same. This is the way to get around that. Are you okay with that? That's a little tweak to yesterday. Now, if you're doing a confidence interval, you don't anywhere assume that the proportions are the same. So you do what you did yesterday. That's right. I did not change anything from what you learned yesterday. But for a hypothesis test, we're assuming that the proportions are the same, so we have to do something. Okay? So here's, in summary, your two proportion z-test. All right? You're going to have your null hypothesis. We talked about that already. We're going to find p-hat pool. We talked about that already. Down here, this is your standard error pooled. Yeah. It shows you the two sample sizes are still different because you have two different sample sizes. That's fine. But you have one p-hat, therefore one q-hat. Okay? Does that make sense? So if you're doing a test, p and q are always the same. Now, once you found the standard deviation in a hypothesis test, you found a z-score, right? Remember, on the formula sheet, it says a standardized test statistic. That's what z is, standardized test statistic. And it says statistic minus parameter divided by the standard deviation of the statistic. So when we did a one proportion z-test, remember, statistic is an estimate. So we did a p-hat minus our parameter was within the null hypothesis, so p, divided by our standard deviation. That's from the one proportion z-test, yes? Well, so same thing has to happen here. All right? What's our statistic in this case? What are we talking about? What's the whole premise of this test? To find the difference in proportions, right? So our statistic is going to be P1 minus P2, or P hat 1 minus P2 hat. Right? It's the difference. Then you subtract the parameter. That's what we think the difference is. What are we assuming the difference is in this whole problem? 0. So every single time you do a two proportion z-test, you're just subtracting 0, so it's really just the difference over the standard error. And it's a standard error, not a standard deviation, because in this case it's an estimate. We have made up a p pooled, right? That's just a standard error of the difference. That's just the notation. All right, So again, it's generally the same thing we've been doing. I just got a little more stuff involved because there's two proportions, so there's more stuff you got to do. Yes. Everyone good with these things? All right, I'm going to do an example, and yeah, it's going to take us a minute because we haven't done one yet. All right. Yes. Okay. Ready for an example? Okay, good. We're reading number 17 from chapter 22. A Vermont study published in December 2001 by the American Academy of Pediatrics examined parental influence on teenagers' decisions to smoke. A group of students who had never smoked were questioned about their parents' attitudes towards smoking. These students were questioned again 2 years later to see if they had started smoking. The researchers found that among the 284 students who indicated that their parents disapproved of kids smoking, 54 had become established smokers. Among the 41 students who initially said their parents were lenient about smoking, 11 became smokers. Do these data provide strong evidence that parental attitude influences teenagers' decisions about smoking? I know there's lots of stuff going on, but we only looking for the two proportions. So in part A, not a trick question, but not about chapter 22, think back. What kind of design did the researchers use? Now, think this through. I'm saying, is it a survey? Is it an experiment? Is it an observational study? I mean, any type of anything. So, okay, so are you sure? It's a specific type of survey, so what kind of survey do you use? It's an observational study, right? Yes, they asked some questions in a survey, but really it's an observational study. Why is it an observational study? Because they see what happens 2 years later. So is that retrospective or prospective? Prospective. All right. So that's one thing I like about our book. It starts bringing stuff back up because you got to think about it. Okay. On part B, write appropriate hypotheses. Now, at this point, we're going to subtract one group from the other, right? And just like yesterday, if I subtract them, I would really like them to be positive because I like positive numbers better. You don't have to do it that way, but I do it that way. So the first thing I'm going to do before I even write my hypotheses is figure out what the proportions are. Because so far in our question, we just have counts, right? So I'm going to figure out what the proportions are. So if you look over here to the side, over here, see this? That's me finding the proportion, right? So the proportion of disapproving parents, kids with disapproving parents, is 19%. And the proportion of kids with lenient parents is 26%. So again, since I like positives, I did lenient minus disapproving. You don't have to do it that way. Okay? So is everyone okay with my null hypothesis? Lenient minus disapproving equals 0. Now, I can see the alternative going two ways. I did greater than, because I'm looking at my sample proportions, right? And lenient minus disapproving should be greater than 0. That's where I got the greater from. But if you go back to the question just says, do these data provide strong evidence that parental attitude influences teenagers' decisions about smoking? So I could see where it could just be not equal to as well. All right, I could see it going both ways. I did greater than. I'll try to make sure your questions are specific on quizzes and things. I don't think it really matters unless they're way more specific in what they're asking you, right? Hopefully they'll be more specific and they'll say, has there been an increase, or do lenient parents let their kids smoke more than, I don't know. But everyone go with those? Yes? All right. Part B. Sorry, C. Are the assumptions and conditions necessary for inference satisfied? So, first thing we need to talk about is independent groups, that we don't forget. Should the group of kids whose parents are disapproving affect the group of kids the parents are lenient? No. So those groups are independent. They're not saying they all come from the school and they're all friends or anything. They just said a group of kids. Okay? So the groups should be independent of each other. What's the next condition? Random. Does it say they're a random sample in the question? No. So do not say the two groups are selected randomly. That did not happen. Yeah. So we assume that the 284 students who indicated their parents were disapproving of smoking is a good representation of all kids whose parents disapprove of smoking. And we assume that the 54 students whose parents were lenient about smoking are a good representation of parents that are lenient about smoking. Make sure you're writing these things. I'm not saying this for fun. I know it's a lot to write. I get it. What's the next condition? 10%. Is 284 less than 10% of all kids who have parents who hate smoking? Yes. Is 54, no, sorry, 41. Is 41 less than 10% of all kids who have parents that are lenient about smoking? Yes. But you need to say those things. Don't just say 284 is greater than 10% or less than 10%. 10% of what? Put it into context. Always. Then we have success failure. We should have 4 numbers. There are 54 successes, if you will, that are people that are smokers out of the 284 that have parents that disapprove. So 54 is greater than 10, and then 230 is greater than 10, right? The other group, same thing. 11 is greater than 10, and 30 is greater than 10, right? So that works. Now, there is another way to do this. You don't have to do it that way. It works fine here. If for some reason, like the second group, it said 9 became smokers. Remember, this is out of a whole group of kids from the beginning, right? You could go back, pool first, and then multiply that pool percentage by the total sample size. Okay? That would work too. That doesn't come up very often, but you could do that. Both groups. Both groups. You would treat it like one proportion at that point. You have enough kids in your sample that it's okay. All right. So are our assumptions and conditions met? Yes. So in part D, test the hypothesis and state your conclusion. All right. So I'm going to switch over here to my work. So because the conditions are met, I can perform a 2 proportion z-test and use a normal model, right? Now, the next thing is to show the standard deviation. What do we have to find before we actually do that? We just talk about. You have to have p-hat pooled. Right? We have to pool the data, figure out our proportion we're going to use in our standard deviation. I always, if you're looking at my homework, because you guys do this fine, my p-hat pooled is always in the margin, because I just do it out to the side. So, p-hat pooled is right here. There were 54 successes, people that were smoking out of people that had parents that disapproved. 11 that were smoking out of parents that were lenient. So 54 plus 11 is 65 over the total sample size, right? That's where I got those numbers from. Everyone okay with that? So p-hat pooled is 0.2. So now I can go through and find my standard error, right? So I've got 0.2 times 0.8 over 284, kids with parents that disapprove, plus 0.2 times 0.8 divided by 41, kids whose parents are lenient. So your sample sizes can be different, But since we're assuming the null hypothesis is true and there's no difference, that's why I have the pooled value. Everyone okay with how I found the standard error? Yes? Maybe? Questions? So what do you find after the standard error? Z-score. Again, it's statistic minus parameter. Our parameter is 0. Our statistic is that we subtract the original proportions. Again, I'm doing this entire question lenient minus disapproving, right? So I'm going to do lenient minus disapproving to get my statistic. So there's that lenient minus disapproving, that's 0.07 minus 0 divided by the standard error. Get 1.045. The difference in the proportion. The proportion from the very beginning of kids that smoked that had lenient parents is 26%, 0.26. The proportion from the very beginning of kids that had parents that were disapproving, it is lenient minus disapproving. 0.26 minus 0.19 is 0.07. You actually just subtract it. Other questions about where I got 1.045. Back up there yonder with my alternative hypothesis. I said the difference would be greater than 0. That means I'm looking at the upper tail of my normal model, right? So I said greater than 0. So I'm going to go from 1.045 to infinity to find my probability, my p-value. Look at this notation very carefully, because some of you guys are messing it up on quizzes, and I've been letting it go, but I'm going to stop letting it go. Capital P, as in probability, capital P, that the z-score, people have been putting p there, the z-score is greater than the z-score that we have. So the probability that z is greater than 1.045. That's what we're doing. We're doing normal CDF. We're doing a normal model. We're talking about the probability that z could be greater than that. Okay, yes. And I got a probability of 0.148. 0.148 is otherwise known as the p-value, right? That's that magic number that we use to make all of our decisions based off. Like we make all our decisions, right? Is 0.148 high or low? So if it's high, we do what? So here we go, over here on the side. Because the p-value is high, we fail to reject H0. The data suggests there is no difference. They're going to be in context like you should. I get lazy. No difference in the proportion of kids smoking. So that means there's no difference in parental influence. Right? That's what it was all asking us about, the parental influence. Questions about that? Again, similar stuff we've been doing. There's 2 more pieces of this question. On E, explain in this context what your p-value means. We've been practicing this. It's a very similar statement. Your p-value is 14.8%, right? So assuming our null hypothesis is true, therefore assuming no difference, then 14.8% of the time, we would see data or a difference like we got here, right? That's not shocking or surprising. So here's a really, this is probably not the most awesome sentence, but that's what I got. 14.8% of the time, we would see the observed difference or a larger difference, assuming there is no difference, assuming the null hypothesis is true. It'll work on how to explain your p-values. So chapter 21 talked about in chapter 22. Last question. If that conclusion is actually wrong, which type of error did you commit? Our conclusion was that we failed to reject H0. If you fail to reject and we're wrong, what kind of error did we make? Type 2. All right, so you're going to have to start answering all these questions You know how to answer them, but I mean, you're going to start putting it all together. You're going to put it all together. That's why I haven't had a million like free response questions I could give you for the last test, because there are plenty of hypothesis test questions out there, but they'll ask you about errors. Well, you didn't know about errors yet. Now you do. Errors will continually come up over and over and over again. Other questions? So, do you think you could handle trying 2 hypothesis tests for homework? Okay.